So in the previous video we were talking about this finding the time period of a simple harmonic motion executed by a normal spring block system, which came out to be t is equal to 2 pi under root of m by k. So now in this clip we are going to talk whether g will affect this time period or not. So the first thing that we are going to do is we are taking a spring. So this is a spring. It is neither elongated nor compressed, so it is in its natural length. Okay, now what we are doing is we are just suspending a block, that is a mass. We have suspended a mass. So this was the normal length of the spring. So what we are finding is an extension, that is x naught. What we did is we just brought a mass and we suspended in this spring which was hanging at its normal length. So when you will hang a load, it will definitely extend. Extension will be observed. So the extension is x naught from its normal length. So in this case, this is in equilibrium. We have just suspended and left. So the mass, due to the mass, a force mg will be acting downwards, and the spring, due to extension x naught, will exert a force restoring on this block. So this force restoring will be k into extension, that is kx naught. So this is an equilibrium, so this force balances this force. So from here we can write kx naught is equal to mg. So this is our first equation that we are getting. So now what we have to take another situation where we have the same spring. Now what we did is that we will just displace this mass by a very small distance, displacement x. So what we are going to do is we are going to hold this mass, we are going to displace it by x and leave. So when we are going to displace it and release, it will execute a harmonic motion. So let's check whether that comes out to be simple harmonic motion or not. So now what we have done is we have displaced this mass, the same mass. So this was its natural length. This was the x naught that came due to the load. Now we have further displaced it by a force. So this displacement is now this displacement is x. So now what will happen is now we have displaced it by x and we have released it will undergo SHM. So let's write equations for it. So on this block we will have a force restoring by this spring upward. We will have a mg downward. So obviously this force restoring will be greater than this mg. So that is why it will perform a harmonic motion. So we can write as that is force restoring will be this the force by the spring, that is k into x naught plus x, that is your total displacement from here to here from its normal length, minus of mg. So your force restoring, I can write it as mass into acceleration restoring. This will be equal to your kx naught plus kx minus mg, right? So now what we are going to do is that we are putting this kx naught is equal to mg. So this will become mg because we have proved this in this situation. So your m into ar is coming out to be this kx naught can be replaced by mg plus kx minus mg. mg gets cancelled. This mg gets cancelled and you get m into a restoring is equal to kx. Now most of you would be getting the feel that it is turning out to be the same situation we have solved earlier. So our acceleration restoring, it's coming out to be k by m times of x. So in the situation of SHM, we have acceleration directly proportional to x. We have a is equal to minus omega square times x, and we have magnitude of acceleration as omega square x. So here if we replace the magnitude, we can write omega square x is equal to k by m times of x. X gets cancelled. We have omega is equal to under root of k by m. Omega, you can write omega is equal to 2 pi by t, and when you reciprocate it, you get t by 2 pi is equal to under root of m by k, and you get t is equal to 2 pi under root of m by k. So you can see that the time period has nothing to do with the g. It is unaffected by g. Hope you liked the video. Thank you very much.